So then we're going to talk about confidence intervals with population variance. All right, well, we should start with what's the symbol for population variance? Yours?
Because the monitor wasn't working. I was actually wondering if I could go ahead and replace it.
Go for it. Can you do it quietly? Cool. And mind you that.
Oh.
So if you go here and just replace it, you're good. But if you start dancing over here,
Okay.
Macarenas, you're going to get caught. Right. Here you go. You do you, boo, and I'll do here. Cool. Just continue. Thank you very much. So there are going to be so much editing right now. All right. So what's the symbol for population variance?
What's what?
What's the symbol for population variance?
Not here.
Oh my God, guys, you have been in this class for about 3 months.
I thought it was. Never mind. Population. I don't want to be wrong. It's this old thingy with
Sigma.
the square.
Yes, sigma squared.
Yeah, from missing class on Monday.
Yes. All right. All right. So let's talk about the chi distribution, chi-squared distribution. Chi-squared distribution looks like this. So chi-squared distribution. Now, if you're wondering how to draw chi is like an X, just one part of it is flamboyant and the other one is straight. Right, so this is what chi-squared looks like. So chi distribution looks the following. It's not symmetric, so let's get some data on it. First one is it's not symmetric, and that's a biggie. First one is it's not symmetric. Second part of it is values are non-negative. Right? It starts at 0 and it touches 0. When you draw the bell-shaped curve, those tails were getting closer and closer and closer, going to infinity. They will never touch. Right? With chi-square at 0, it actually touches.
You say it starts with 0?
Yeah, it starts at 0 and then keeps going forever. But it starts at 0. We define chi-square as the following formula. N minus 1 s squared divided by sigma squared. You good?
I need to get
Oh,
some.
okay. That's the formula. So what's n minus 1? Guys, she's excused because she wasn't here, but n minus 1. What's n minus 1? df is degrees of freedom, right? N was sample size. But we defined n minus 1 as as degrees of freedom. Okay, what's S squared? What's S squared?
Sample variance.
Sample variance.
It's right here.
Sample variance, and then sigma squared is population variance. We note that as the degrees of freedom increase, this shape of this will become more and more symmetric. So let's increase. And there's one last piece of this. When we're looking at the chi distribution tables, almost every single one gives critical values. For area. So the last one is gives critical values for area to the right. Z-score was to the left, right? Chi-square is to the right. That's the reason why I'm trying to keep chi-square as a separate lecture, not combining with others. Okay.
It says give critical.
Gives critical values for area to the right. So if I have some critical value here, what it will give me is this area right here. Right? So it gives us area to the right. Right. What do you say we do an example? Oh, finally. You still copying? You good? Okay. In that case, let's do this one. Example. N equals to 12, 95% confidence. Level, find critical values. So sample size 12, confidence level 95%, find critical values. Easy enough, right? So what do? Well, we do it the way we always have been doing, which means we start with a picture. My chi-squares aren't as beautiful as my standard normal, but This is still 95%. So somewhere in the middle of this is our confidence level at 95%. Which means our alpha is what? Our alpha is 0.05. Yes? At confidence level, the complement of the confidence level. Right? Because this is the confidence level. This is 1 minus alpha. Okay. So if alpha is this section and this section will still occupy the same amount of space. Right? This is bigger, but this goes forever. So this little part is alpha over 2, and this little part is alpha over 2. Well, how much is alpha over 2? So far, everybody's with me. Aside of the fact that the graph looks slightly different, all those steps we have been doing before. Yes? Yes. Good. So here comes, we're going to have some critical values. Chi-square. We're going to have some critical values here. Now, those two will be different. They are not symmetric. Right? Before that, we had a 0 in the middle, and they were symmetric. This time around, they are not symmetric. Because they're not symmetric, I'm just going to add a little indicator for myself, so I know they are not symmetric. Right? I'm just going to say this one is the right one, this one is the left one. Okay. All right. Now we're going to take a look at the table. Chi-square has. Do you have 1 or 2 chi-squares? We have only 1 chi-square table. What?
I was wondering what you were saying.
Chi. What did I say? Chi.
It's pronounced chi. So chi-square, if you look at it, it has degrees of freedom on the left side. We know how to deal with those, right? And it has an area underneath it. So let's look at which areas we are actually talking about. So we want this area. And how big is this area? This area is 0.025. Why am I pointing the arrow to the right?
Because there's a lot to chi-square.
Because chi-square gives you to the right. So what's the critical value here? That sounds about right. 21.92, yes.
Because alpha is, EF is 11, right?
Mm-hmm. Is everybody comfortable how we got there? You got it? No? You're looking up this, so you're looking up at the top, you're looking into the third column from the right, right? Third column, 1, 2, yes, from the right. And you're going down to n is 12. So in our case, let's put this here, df would be 11, because df, degrees of freedom, is divided as n minus 1. So if you go down to 11, got it? Good. Everybody else with me? Yes? Good. So how do we find this one?
Let's go back. Can you use
No.
Is that the 0.975?
Yes. We're looking at, to find chi for this area right here, right? But we would consider alpha over 2. We cannot measure this distance. What we are looking at is this, because the area is measured from the right. So we start walking from the right, we walk, 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 till we get to it. And that would be 0.95, which is the middle part, plus 0.025, which is this part. I add this to get the total, which in our case comes out to be 0.975. Right? So now I'm looking df degrees of freedom at 11 and 0.975. Okay, so 11.975, and I get a 3.816. Is everybody with me?
How'd you get the 3 point?
This, I looked up this probability. This probability, because it measures critical values for area to the right. So I start at positive infinity, I keep going back, 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 back. Here's my 0.025, and then here's 0.975. So I'm looking 0.975. So critical values are Is everybody absolutely sure they got this? Good. So, people steal my favorite eraser. Good. Excellent. Thank you. Is it raining?
It's just windy.
Okay. Okay.
Why is chi-square right greater than chi-square left? I mean, we're looking at area, right?
Yeah. No, this is critical value. Area is smaller. Right, this area and this area is smaller than this whole area. Right, this area here and this area are the same. But this is a critical value. So, let's look at the confidence interval maybe. Maybe that will help. Remember that chi squared was defined as n minus 1 s squared divided by 6. While remembering this, I erased it, so yeah, you guys have it on now. We're gonna move it around till we get sigma out of this. If we get sigma out of this, we get n minus 1 s squared chi squared. Okay. So, something doesn't sit right with you. Those two look very similar, aren't they? And here's the biggie. Before that we had x bar minus e, x bar plus e, right? We differentiate. In this case, we're going to differentiate because we have two different chi's, right? You have two different chi-squares. You have two different critical values. So which one goes where? This number is smaller than this number. Everybody's with me. This number is smaller than this number. Right? This is bigger than this. The signs are telling us that. Which means that this fraction has to be smaller than this fraction. Which means that if the numerator is the same for both, then this denominator has to be bigger than this. Right? 1/7 is smaller than 1/3. Which means that this is right, this is left. Right, left. Good. Can we get a confidence interval for a standard deviation? Can we get a confidence interval for standard deviation? Yes, we can. What's the symbol for population standard deviation? Canon. Regular canon. Right? My sigmas are getting awful. So if this is standard deviation, I just screwed it, which means that. Okay. And this is it for chi-square. There's not much more to this topic than this. This is it. So, couple examples? Yeah, okay. Come back. So a couple examples. So we take a sample of 10 applications, whatever those applications are measuring, and we get a standard deviation of those applications to be 0.15. Construct a 95% confidence interval for sigma squared and sigma. Well, it's statistics, it's a problem, we don't understand it. Picture. It always starts with the goddamn picture. We're going to put the confidence level in the middle, which is 1 minus alpha. Which in our case is 0.95, which means that this area over here is alpha over 2 equal to 0.025, and this is alpha over 2 equal to 0.025. So what are our chi's squared? Let's find the critical values. Well, this chi-square is responsible for 0.025. Uh-huh. 19.023, yes. And then we have a second chi-square over here, the left one, and that's responsible for 0.975. Mm-hmm.
So to get 0.975, it's 0.95 plus 0.025, right? That's all left.
For this?
Yes.
Yes. That's this plus this. So what's our confidence interval? It's n minus 1, s squared divided by chi squared less than sigma squared less than minus n s squared divided by sigma. Sorry, s squared divided by chi squared. And this is the right one, and this is the left one. So now we just plug it in. So that's 9 times 0.15 squared divided by 19.023 less than sigma squared less than 9 0.15 squared divided by 2.7. It's easy to forget the squares, try not to forget the squares. You checking me? Okay. Alright, so we have the variance. Confidence interval for the variance. So how do we get the standard deviation? Yeah, we square root the whole thing. And so what's the written answer, if we had to write an answer for this? How would you write an answer for this?
We mentioned critical value.
No. You say, I don't know what the population variance or standard deviation is, but I'm 95% sure it will fall between those two values or those two values. Cool. More problems? Sorry? One more? How about we do a bigger one, more complicated one? Okay? So, complicated. Complicated example. Let's assume miles per gallon for a car are normally distributed. Let's make that assumption. Here. Welcome to the glory of chapter 4. Assuming miles per gallon are normally distributed, a sample of 26 cars has an average of 24.6 miles per gallon with a standard deviation of 3.7 miles per gallon. Construct a 90% confidence interval for the population mean and standard deviation of miles per gallon. we've been toying around the fact that samples are great to describe populations. Here it is. I took a sample. 26 cars. That's not very difficult, right? You ask 26 members of your family to tell you how much they spend on gas per, how much they drive, how much gas they use. That's not very difficult to do. 26 people, it's not very difficult. And having 26 points of data, you can get an average and you can get a standard deviation. Again, calculationally intensive, but not very difficult to do. Right? We could do it by hand. We could do 26 pieces of data and find a standard deviation for 26 pieces of data. Or we can use an Excel program or whatever, but that's not very difficult to do. And now I'm asking you to tell me something about the population of cars. And suddenly, right, here comes the power of statistics. I asked 26, and I'm going to be talking about the population of millions. The only assumption is, I'm assuming it's normally distributed, which is not a very difficult assumption to make. Let's say we had a measurement from 10 years ago and the gas usage per mile was normally distributed. Then we assume it's going to be normally distributed now. So let's do it. There's two parts to the problem. Well, there's part one, which is mu. And there's part two, which is sigma. Right? I'm asking for the average population mean and the population standard deviation. Which one we want to do first? Mean? Mean. Okay, let's do mean. So how do we do it? Well, we know that it's x bar minus e less than mean less than x bar plus e. And we know that e is defined as, and then we have two choices. Well, there are three e's that we know, but one of them deals with proportions, and this is obviously not a proportion. So we have two choices. Right. Or let's write it out. We have three choices. We have z alpha over 2 sigma square root of n, t alpha over 2 sigma square root of n, and we have z alpha over 2 p hat q hat divided by n square root. If you're looking at your formula sheet, this is what you have. You have e in three different variables. We know one doesn't fit in right away. Right? We are talking about means, standard deviation. We're talking about means and standard deviations and not proportions and not percentages. So it means that the last one is out at the very beginning. And so questions, what do we have? What do we have here? What kind of information are we given? Ooh, I made a mistake. Ooh, nobody caught me. Yes. So that was a mistake.
Given 3.7 standard deviation.
Yeah, which standard deviation is this? S or sigma?
That's sigma. Or the circle, right? Or no?
A sample. This is a sample standard deviation. A sample standard deviation is this. Right? So just by looking at the problem, we can get rid of one of the margins of error, and then we can decide which one based on this. A sample has this with this. There's our magical statement which has all our data in it. This has all the data in it. Okay. Okay, well, so let's write it out. Do we have x bar? We do. 24.6. Do we have E? No, we calculating E, mu we're looking for, x bar we have. E we're looking for, T alpha over 2, not yet. We have S. and S is 3.7, and we have N, and N is 26. So the question is, what's T alpha over 2? How big is T alpha over 2? Did you just say 25? 0.05? How do you know?
It's 90%. You're gonna 10% divided by 2.
So you're saying alpha over 2 is 0.05, not T alpha over 2.
Yeah, she's saying alpha over 2.
Yeah. Okay. So let's look at it. Well, since we are dealing with T, we should probably acknowledge the fact that we're going to need df, which is n minus 1, which in our case is 25. And we're dealing with t-score, so what do you guys see? T-score. T-score. And how much were we getting?
2.064.
1.708.
No. You're looking at which table?
T.
And you're getting 2 point? You sure?
Let's look at the T
Okay.
distribution table on the front side.
The one on the back.
And I'm still
Conference the
not getting. I get
2.06.
Yeah.
no.
Okay, 25.
should be 24. We're looking at
No, it should be 25. DF is 25,
26 cars. Okay.
right?
Yep.
25. And okay, so let's do it. Alpha equals to 0.1. So alpha over 2 equals to 0.05. So when you're looking at your table, you're looking at second column, right? You can look at no, flip.
Either one is okay?
No, hang on. This one is okay,
Oh, so it's 1.
but because the next one is chi squared.
Also, is it gonna be one?
That's correct.
So
1.708.
0, yes. 1.708. Regardless of which table you look at, it should be there. 1.708. Did you find it?
You see how
Oh yeah.
Did you know how to get it?
I mean, I just heard him say the answer.
DF 25,
Huh?
and then what they're looking here is
Oh, so
looking at this.
yeah,
Right.
we'll be looking at the third row because the confidence level was 9.
Thank you.
Right.
Yeah. 17.
You found it?
Yeah.
Good.
And then
You found it? Okay. We're using the T table, so this is Z. So we're using the T table, which is either this one or this one. So we're looking at confidence 90%, right? And DF, degrees of freedom at 25.
Okay, 7. What symbol is that?
D,
Is that U and
which one?
this 1.7? Is that a T and
T alpha over 2. Like we remember we did Z alpha over 2, it's just T alpha over 2.
okay, so
So we have degrees of freedom, which is n minus 1 at 25.
1.7.
Yep.
So this.
Yep.
Okay.
So you do the calculation right here, right? You do the degrees of freedom is n minus 1, so it's 26 minus 1, so that's 25,
Okay.
right? So you're looking at this, and then just your confidence level. There's a confidence level, 90,
Okay.
which is this. And the notation is T alpha over 2.
T. Okay.
Good? Good. Uh-huh. You found it?
Yes, thank you.
Good? You sure? Everybody? Right. Cool. All right, so we have T alpha over 2. We have the critical value. So let's find E. So E comes out to be 1.708 times S, which we had at 3.7, divided by square root of n, which is 26. And because I can, I got this. Yes?
Yeah.
No? Okay. So we have E, so let's figure out this. So minus this,
23.36.
so we have, I'm just going to put it over here. So 23.36 less than mu less than
25.839.
8.4. And here's a confidence interval for the mean.
What did you get, 23.36?
X bar minus E.
Oh.
Good? Everybody's with me. All right, so let's look at the part 2. Let's find sigma, or the confidence interval for sigma, since we don't know what sigma is and we cannot figure out unless we do the census. So what do we have? Well, let's start with the critical values. Right, we have those two areas as alpha over 2. So what are the critical values? Again, our n is 26, so our degrees of freedom are 25. So we're looking at degrees of freedom 25 and 0.05. I got this one for the first one. Because I'm looking here, I'm looking for this space right here, which is That's the area. Right? That's alpha over 2. I'm looking for this area. The critical value associated with that is this. Second one is over here. That one is responsible for 95%. Why 95%? Because there's 90 here, 5% here, plus 90, 95%. So this critical value answers to 95%.
14.611.
I'm going to write it bigger. So the left one is responsible for 95, and that comes out to be 14.611. Is everybody comfortable getting those two values? And I got them from here. 95, right? 95 and 25, which is this one, and then 5 and 25, which is this one.
This one.
37.652. So here.
Okay.
Right, this is telling you about the area to the right. So we're going first hitting the first one, which is 5%, and we're going to go to the second one, which is 25%. Sorry, which is 95%, which is right here. Right. Okay, cool. So we have two values. So now what do we do? Well, the formula, which is n minus 1 s squared chi right squared less than sigma squared less than n minus 1 s squared divided by chi left squared. That was for variance, right? So if we want to convert this to standard deviation, so let's plug it in. 26 minus 1, 25, times s squared, 13.69. Okay. That's s squared. Divided by 652. That's less than 25 times 13.69 divided by 14. Ooh, I'm getting ahead of myself. Sigma, and we need a square root. Yes, to two decimal places. Sorry?
Then 20.42.
9 3, I got a 3 here.
No, I got a 9.
9 after the square root?
Oh, no. Yeah.
Yeah. I had 3.0.2.
That's what
No, it's 301.
big square. Yeah, I just found the big square.
If you're calculating this for variance first and then you're going to square the raw numbers, that's fine. Right? But if we are doing standard deviation, we have to square it.
Yes.
We have here.
Oh,
So I got 23.4, and then I'm going to square root it. And that comes out to 4.84. So what's our answer? Well, we don't know what the mean and the standard deviation for the gas consumption is, right? But we are 90% sure that it's going to be somewhere between 2336 and 2584 miles per gallon on average, with a standard deviation somewhere between 301 and 484 miles per gallon. And that's a complicated example. No, but this is as complicated as things get. The worst I can do afterwards is ask you if something would be unusual. You take the biggest of this, and you take a look at one side, or you take the smallest, right, and the biggest, and you draw it the other way, and you have a range of all the possibilities to be usual. But this is about as difficult on a bonus question I can get from this. Right? So my rule of thumb is if you can get this problem by yourself in about 10 to 12 minutes, you're in a really good shape. If you can get this kind of problem and you tear it down in those two ways.
If you keep it in that format, but just change the numbers.
Yeah.
And
I'll probably do. Right? Again, I cannot very much alter this because you're limited by what your t-table and your chi-square gives you, right? But I could give you a population standard deviation, right? And then since you're using z alpha over 2, right, as critical value, I can do whatever I want with this. But this is about as difficult as it gets. But this is also very powerful. Because now you can look at a car that you're trying to purchase, right, based on your statistics. You can look at a car that you purchase and say, hey, your gas mileage is unusual. If I told you I have a car that burns, what? No, I was going to go with 32. No, let's go 30. Let's go 37. If I told you I have a car that burns 37 miles per gallon, is it unusual? Is this an unusual vehicle?
Yeah. Two standard deviation for 3.7.
Right?
Yes.
Population standard deviation is off at most this much with our confidence level. At most this much. So you can be 90% sure that 2 standard deviations away from this, and this is farther. Right? And this is a bonus question. This is one of those style bonus questions. Is this unusual for what you got? And you can say, hey, I'm 90% sure this is unusual. Why are you 90% sure? Because this range, and this range is based on this confidence level. I change that to 95% or 99%, those two ranges will get very wide. I change it to about 80%, those ranges will go very narrow. Right? The same rule applies. But at 90% confidence, this is unusual. But this is a bonus question, right? This is as difficult as I can ask anything from it. Now again, since we don't have exam 2, we have just the final. This is a question that can end up on the final. This is one of those big questions on the final. This, looking exactly like this. Can you solve this? That section is done. Right? Because I'm going to ask what? We have 5 chapters, plus I'm going to try to cover correlation and regression. So 6 chapters. We're going to cover about 6 chapters altogether. The exam will have, final will have, I don't know, 12 questions for 2 hours. That's 2 questions per chapter. That's a question per chapter. Right? This is as difficult as it gets. Right?
Can a note card be bigger than 3x4?
Yeah.
4x6.
It's really, you have the table, you have the formulas. At this point, I don't think it matters how many cards you have, because if you cannot squeeze it on one with the tables in front of you, and your tables, last time I checked, come with a formula sheet right on the beginning of it, just in case you forget. If you cannot get it on one card, I will be becoming, very, very worried. Because it's not like those formulas take a lot of space. Either you know how to use it or you don't. Right? If you need to write an example because there's something just doesn't click, chi-square doesn't click, you take one side of that index card and you write yourself an example. Okay. More? Should we do one more?
Where's the 13.69?
This is s squared, which is this, 3.7 squared.
Oh, yeah.
Yes? You have it.
No, I had it as 13.69 squared. I realize it now.
Oh, awkward. Okay, one more?
Yeah.
Yeah, okay.
Can't be not so complicated.
Let it be complicated.
But this is not complicated, it just takes a
It's
while.
already complicated.
Practice.
That's how we see it on the
Right here.
No, that's a bonus. I'll probably never get to the bonus.
Well, the bonus will be, is 37 miles unusual? Miles per gallon, that's a bonus. Is 37 miles per gallon unusual? That's a bonus question. This isn't. It's just 2 questions to combine it into one. Okay, where's my marker? Okay. Yes, steak.
Steak?
Like food?
Yeah.
Oh, steak.
Oh, like steaks.
No, not like vampire, like food.
S-T-E-A-K.
S T-E-A-K.
I thought it said.
Fine. Here, you have your E's. Now back to work. Construct a 99% confidence interval for variance of steak food size in an all-you-can-eat restaurant, knowing that 13 patrons reported their steaks to be on average 6.81 ounces, 6-ounce steaks or 7-ounce steaks, right? With a variance of 1.27 ounces. You want a real example? Here's a real example.
Are you hungry?
Yes, I haven't eaten anything since 5 o'clock in the morning.
Really?
Well, I had something that resembled acai bowl. I still don't know what an acai bowl is, but it had yogurt, so it was nice. God, I would kill for a steak right now.
He's treat for himself.
Well, I'm going to cook one. I'm going to go get a nice piece of sirloin. With mushroom sauce and mustard and
Mustard.
yeah, I make a really awesome steak Day18.
Let's just leave. Don't need to do this question.
So how do we do it?
Variance.
Draw the picture.
I love the attitude. Sure,
Start labeling.
sure. Let's draw a picture. She said to draw a picture. There's a picture.
No, I think we need to first identify what is
Simon,
what.
just draw the
Yes.
damn picture.
Number is 13.
So what do we have?
Yeah, take variable then.
N equals 13. Great. What's next?
Degree of freedom is 12.
Okay, degrees of freedom is 12. You're expecting a t or chi-square. No problem. What else?
A over
1.27 ounces.
alpha over 2 is 0.005.
Alpha, let's go with alpha first. But alpha over 2 is 0.005. Okay.
Or alpha.
We're looking at means as 1 point, no, sigma is 1.27.
Sigma? What sigma?
Variance.
Variance
Oh,
is it?
I'm sorry, standard deviation.
Oh, x bar is
So let's start with x bar. X bar is, that's x bar, right? That's the average that they're reporting, right? And they tell you a variance, but this is a sample variance.
so s.
Uh-uh.
Oh no.
S squared. S squared is variance. Right? S is a standard deviation, S squared is variance. Variance is squared, the square of standard deviation. Okay,
So we need to find E.
Everything.
well, hang on, what are we looking for? What is it asking?
For
If you're talking about E, you're talking about the mean. But this is asking you for variance. Right? If you are looking for variance, then we're looking for that, right? This is a confidence interval for variance, which means that now we can draw the picture because now we know which picture we're drawing. getting really excited about drawing pictures. I appreciate that. I really do. But
Take us in handy.
you'd be surprised how many exams I get with pictures drawn on pages or in the corners or flipping the table or something. ASCII flipping the table, yes. I get those a lot. All right, so now we know that picture has to be of chi-square distribution, which means it's this one. Right. We know that alpha over 2 is 0.005, 0.005, because the middle is 99. So we look up.
Going that, yeah.
I thought you guys knew everything.
Then we find
I two, right?
the chi table,
Chi squared,
chi-squared table.
chi squared. Chai. I would kill for a milk tea right now too. Milk tea.
Oh, milk tea, I love it.
It's pronounced Kai. Like, how is this not read Kai?
No, when I think of Kai,
Kai
I
is
think of AAI. I was
yeah,
looking
this
for
is
Kai
white.
the whole time. I was like, oh, you know, this one works. Let's go with this one. So, okay, it's spelled Chai. But it's not English.
I hear you snickering over there.
I was typing in Kai over and over. I was like, no, I don't want that.
The Earl Grey table. Let's get the Earl Grey table. All right. So first one comes from this little section, right? Because the tables are read from the right. So 0.005 at degrees of freedom 12, we get,
0.055.
yeah. What did you get?
28.3.
28.3. You're not British because you're not on the chai time. This is so going to get recorded. And I'm not just going to be too lazy to edit it tonight. And you got the other one to be 3.5. 3.5.
4.
99.
12.
99.
No, it's 99.5 because this one is 0.995 because you have to add to get this critical value. You have to add this plus this. Is everybody with me?
Yeah, what do we square? Do we square at the very end?
What? This?
Formula, yeah.
This? No, we don't square those. This? We don't square it.
That's for standard deviation.
For standard deviation, we take a square root. We don't square, we take a square root.
Wait, so would the 1K27 already be?
This is already squared.
Oh, okay, so I can just put it into that.
Yeah, it's one of those, I'm making it easy for you and you're still going to square it.
Yeah.
You good on the table? Found it?
I think so.
So 0.05 at 12 is right here,
That's what I was looking for. And then 3.07.
right? Because this is 99 plus that low section that we said. Good. Good, 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 good.
Yep.
Yep, yep. Oh, yeah. I noticed that the moment I walk between the desks, the laughter just kind of stops. Now I turn my back and just everybody snickers. All right, so let's plug it in. Which one do, I didn't label. Which one do we plug in where?
Put the very
Right is first. Right is first.
Bigger is first, right? Because we want to take a smaller fraction. So we have n minus 1 is 12 times 1.27. We don't square it because it's already squared. This is already squared because it's already variance.
Oh, God. I was about to say.
I'm making it easier for you and you still square it. It's like hopeless. That's okay.
Oh, that's gonna screw me up.
That's why before you start doing the problem, do this. Write this out.
Yeah. And that's still square.
Yeah.
That's okay. Look, the reason why I'm throwing you curveballs while we are talking about it now is because the chances of you doing it again later are much slimmer. You don't do the same mistake again. All right, and this is over 28.3, and that's smaller than squared, smaller than 12 times 1.27 divided by 3.074. I got this.
Is it still squared in the middle?
Yeah.
Or no?
Oh, that should be squared. Yes.
Oh, it's still square?
Did I make a mistake somewhere? Oh,
No.
You just forgot that.
Just forgot.
just to put it square. It's just a square.
Was that a test?
But don't you square it?
What? I will square root it if I want to get a standard deviation, but I want variance in this case.
I thought you said just round it to the second digit. Third digit?
Rubin's.
I have 2 digits here, two decimal places here, so I'm rounding to the third.
If you wanted the standard deviation, you would square root it all.
This is a good example. It needs to be under test.
So I would just do this. If I want a standard deviation, I would just square root all of it. Right, that turns into just sigma, and then square roots of those gives you a standard deviation. And again, the explanation is, I don't know what it is, but I'm 99% sure it's between, the variance is between 0.539 and 4.958.